Here's a problem someone asked about from chapter 11. I'm going to focus here on part B. And so part B wants to know, so there's a person, a physics student or something, they're up here at the top with a spring of K constant 80,000 newtons per meter, a mass of 100 kilograms, and the spring is compressed 0.50 meters. And it's shot off, and the person's going to slide down this hill, and they want to know how far up this incline they're going to go. And so I'm going to call that distance up the incline to be D. And so there's two parts to this problem. The first part is finding what the velocity of the person is going to be right before they start sliding up the incline. And so for that situation, you can conserve mechanical energy. All right, so I can say that the energy initial, energy final equals the energy initial mechanical energy style. And you can do this different ways. I'm just going to do this looking at the person right before the spring shoots off. So initially, the person's going to have some spring energy, 1/2 K delta S squared, and then they're going to have mg, I'll call this the initial height. And of course, the initial height I'll call 10 meters. So I'll call the height final, okay, down here, height final equal to 0. So this sort of position down here at the bottom is height final equals to 0. So afterwards, all their energy will be in kinetic energy. All right, and so what we do here is we take this equation and basically go through and plug in our numbers and solve. It's kind of a little bit of a long one. And so I'm going to divide both sides by mass, multiply both sides by a 2, and then finally I got to take the square root of all this garbage in here. Okay, so I do that. So you got the K is 80,000 newtons, delta S is 0.5, and then mg, the H is 10 meters. Okay, so you get like, when I do this, after I plug everything in, I got 19.8 meters per second. Again, that's from conservation of mechanical energy. We know that because the only things acting here are that spring and gravity until they reach the incline. Now, once they reach the incline, there's friction, so we can no longer conserve mechanical energy. And so what we need to do is we need to look at, and again, I'm trying to find the height D, it goes up. We need to look at the forces here. And so the forces, we've done incline forces, so it'd be a normal force here, and the mg splits down into two pieces. So it's mg cosine theta here, and then this one here would be mg sine theta. So that's that guy right there. And then the other force we have to account for is the force of kinetic friction. And so I'm interested, again, in the direction, so I'll call my x and y sort of like this. This is the y, this is the x. I'm interested in how far up in our twisted x direction it goes. And so what I'm going to do is I'm going to find the net force in our x direction. So the net force in our x direction would be negative force of kinetic friction minus mg sine theta. And we know that our force of kinetic friction is going to be mu times the normal force. And this is a situation where we can see that the normal force balances out mg cosine theta in the y direction. And so our very complicated forces are going to look like this here. So that's the net force. Now, one way to do this is to solve for the acceleration and then take one of your kinematics equations and solve for the distance that it goes up. You can totally do that. What I would probably do is I would look at the work. And I know work is something that's sort of new for everybody, but here's how I would do it. So the work is the net force times the distance. And so it'll be mu mg cosine theta minus mg sine theta, that's the net force, times the distance, would equal kf minus ki. Well, kf is 0, and ki is 1/2 mv squared, where again that v is just that 19.8 that we started with. Okay, so if I draw like another picture of the diagram showing you the kinematics of it, so the block is going to go up some distance d, and it starts with, I'll call this the initial velocity, and ends up with a final velocity equal to 0. And of course the initial velocity is that 19.8 we just found in the first case. So what happens is in this problem the masses cancel and also the negative signs cancel, And so I get this equation that's more like this: mu g cosine plus g sine divided by d equals 1/2 vi squared. And if you solve this for d, it's kind of nasty. But I got something kind of like this right here. Again, you can do this with kinematics. It's kind of up to you, but the nice thing about work is you kind of get this in one little step. You don't got to find the acceleration and then find everything else. But if you plug in there, again, what we're plugging in for the velocity is at 19.8. The mu is 0.15, I think, and the angle is 30 degrees. So if you plug that in, and I get, when I do that, a distance of about, when you round up, 32 meters up that incline.